Okay, hi. This is going to be an example of what I like to call the titration megaproblem. So the whole goal here is to walk you through all of the phases of a titration curve for a polyprotic acid. Now, we could do the same thing uh, for a basic substance as well, polybasic, I suppose. Um, we could also do this for a monoacidic or monobasic. We could do it for a strong acid or strong base. But I'm going to show it for a weak acid that's polyprotic, while also pointing out some of the ways that you could turn this into a shorter problem for some of the simpler cases. So hopefully that'll be a useful thing for people to look at as they're working through one of these longer problems. I'm also going to try to avoid doing this as something with a lot of pausing and editing, specifically because I want it to be at the same sort of a speed we'd have in the classroom, which means that sometimes it might be a little longer than it needs to be, but I think it's going to give you time to follow along and digest it as we go. And if you're trying to follow along on a piece of paper, it gives you a chance to do that. And in fact, if you want to try following along on some paper, now would be a great time to pause me, go ahead and grab a couple of sheets. That way you're going to be able to go through and see all the steps that I'm doing and try them out yourself too. That's always a great try. Attempt is to say, hey, let's just go ahead and hear him set up the problem, try out the problem, and then hear how he solved the problem to see if you're doing it right. That's a good approach when you're studying these sort of things. Now, we're going to start out with phosphoric acid. You can see here that I've got the conditions already listed out. Sorry, I got to wake up the pen. Here we are. Listed out up here. So we're going to start with a formal concentration of 0.1000 molar. We're going to go 100.00 milliliters for the volume of that. It's going to be our triprotic acid, phosphoric acid, and it has these three different pKa values for it. You can see here this one is getting to be really far over on the spectrum. Remember that our spectrum for acids in water, it kind of taps out at 1 times 10 to the minus 14 because that's Kw as well. So we're already getting to the point where that last proton is sticking on just about as well as water is sticking to itself, right? So we're going to have not a whole lot of effect from that one in this problem. That'll be something that factors in a bit. Now let's assume that our titrant is going to be coming in at the same concentration. Now realistically in the lab, that would be a bad choice because notice how much volume of titrant we're going to need. It would make a lot more sense for us to bump this up one order of magnitude or so that if we're doing 100 milliliters for our analyte, we can finish the titration in about 10 milliliters or something like that. There are some practical considerations in trying to make sure that the actual hands-on at the bench approach is going to give you a really good quality measurement. So those are something to think through a little bit as you're imagining this. But let's just kind of do a quick little cartoon sketch, a very bad, oh wow, a worse than usual cartoon sketch of the burette. So it's slightly humid in my office, which is making my hand stick to the stylus interface a little bit, which is making it even worse in my drawing, but you know, we'll live. All right, once again, kind of a crude version of a burette, but we got the key things here that we know have to be there. Now I'm going to draw the flask over here to the side, just making it clear that we have this flask and what's going to be in the flask. Let's try that one again. Still, oh, all right. We're just going to do this as lines like this. That way I can erase individual pieces and not have to erase the whole thing. Okay, it's not the worst flask I've drawn. That was the last three that I drew. All right, so in this analyte, in this scenario, we're going to have some sodium hydroxide down here. And it's already dissolved, but I'm just going to show it like it isn't for a second, just to really get across that we have our sample down here and it's living in some water. In fact, let's even go ahead and use color to our advantage here. Great. So it's sitting in some water down there, right? So we've got it dissolved and dissociated and it's ready to react. Now up here in the burette, we're going to have our H3. Actually, sorry, I said it backward. I said we were going to put the titrant up here. So titrant is going to be our sodium hydroxide. That does make a better sense here. So in the titrant, we're going to have our liquid phase. Again, I guess I'll go blue. There we are. So we have our sodium hydroxide here. Sure, why not? And then down in the flask, that's where we're going to have our phosphoric acid. And phosphoric acid starts out as a liquid / aqueous anyway, so it'll be fine. For some reason, my pen just stopped responding at all. Okay, now it's back. Good. Now I'm going to switch this back over. Okay. Now, let me walk you through the process of how we figure out the important parts on this titration curve. Now, I'll try to come back to this page as the location where we have our graph paper. And so I'll put everything in on this graph paper, but I'm going to use the blank pages that I have in this PowerPoint file to do all the math work that we're going to need. I'll also occasionally pop over to Excel and use that as my calculator while we're going through this calculation. Okay, so we have our sodium hydroxide filled up. We're not going to worry about drawing lines on it or anything. Now let's imagine that we have a pH probe sticking down here into our flask as well. All right. I'll cheat this way. That way I don't have to worry about drawing good lines. There's my pH probe. Okay, now I got a pH probe in there. We're going to be careful not to have the stir bar break the glass bulb or anything like that. I'm not going to draw the wire showing it connected to the pH meter. We'll just go with it, right? But as a result, over on this axis, I'll be able to keep track of my pH as I go. So let's see, 1, 2, 3, 4, 5, 6, 7. Actually, it gets a little hard to see the gray lines. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I have 10 dark lines along here. So I'm just going to start out at like a pH of 1 at the very bottom. I know it's not quite perfect, but it's all right. I'll just do it that way anyway. Leave us a little bit of space on our graph paper. I'll just put this as being pH 1. Notice it should go down to 0, but I'm going to start it with an abbreviated axis. All right, so I'm just going to quickly label these. Wait, let me see. 5. There are 6. See, some of these are bold, but not very bold. So I'm going to still make a little tick mark so it's easier to find with my eyes as we go on. And that'll work well enough for the range that we're actually going to care about. Now remember, to get to pH of 0, we've got to have a fairly concentrated, strong acid in order to get there. And at that point, we're going to start not care as much about the pH because we're just in such concentrated acid that it's just acid. It's just going to be really acidic. Enough so that we have the leveling effect of water at play and some other practical considerations we have to worry about. And so there isn't, oh, and also I'll point out that the pH meter has a terrible ability to measure pH below pH of 2, really, and even a bit above that. And that's something we'll bring up later on in our electrochemistry units, talking about how they actually work. And it also comes up in the instrumental analysis class for most people when they go through how the pH meter works. For now, I'll just point out, after you get to about pH 2, anything below that, you're kind of pretending to know what the concentration is because you're perturbing your equilibrium by having such a high amount of pH, the concentration of H+, all these other issues. So again, if you don't love that I didn't start at 0, it's a pretty practical result. And even then, remember that we're talking about a log scale for concentration over here anyhow. Now, on these other pages, I've got the important experimental details already written down. But let me just point out, in a second here, we're going to figure out what volume we need to titrate each of our protons. Let's just go ahead and start out by realizing that there's going to be an equivalence point. The equivalence point is when I have the equal number of moles of the reactant and the titrant, or our analyte and our titrant. So I could actually calculate that out, and in fact the math would be pretty easy here because I kept them equal molar. That's one of the reasons I like to have them equal molar for these problems, even though it's not experimentally quite relevant. But I'm going to do something even more generic. I know that I've got a triprotic acid, so whatever my equivalence volume is, I'm going to hit that volume, double that volume, and triple that volume for each of our 3 equivalence points. Now, if you're noticing I'm using the word equivalence point, remember, equivalence point is the moment they're equal molar for the 2 reactants. End point is the moment that you see that they're equal molar with whatever indicator you're using. And they should be the same thing, but experimental considerations play into that. So equivalence point and end point are going to be slightly different, though they should be the same. All right, now anyway, Since I've got 3 Kas and 3 protons I'm titrating, there's going to be 3 endpoints. Now let me just see how many divisions I've got coming along this way. I'm just going to make tick marks to keep track. Got 2, got 4, got 6, 8, 10, 12, 14. So I got 14 little tick marks to work with. Let's see how many regions I need. Okay, so I need to have maybe 1, 2, 3. So that'd be my third equivalence point, and then I have a little bit of aftermath. That seems like it's going to work out pretty well. So I'm going to have this be my equivalence volumes, just to keep track of them down here. So I'm going to get rid of these little little marks made to guide my eye. And I'm going to put VEQ1, VEQ2, and VEQ3. Those are my equivalence volumes. I'm going to put real numbers on this axis in a little bit here, but just so we can start sketching things and seeing how they also can be done in a pretty quick generic fashion, let's do that. Now the other thing I'm going to do before I get to the math of it is let's take a second here to actually think through what all of these should look like as a quick sketched titration curve. Sketching a titration curve is a really important skill to have, and it's a bit separate from just solving it numerically. So let me just go ahead and I'm going to grab Excel open here for a second. Now let me type in my Ka values. I've got 7.11 times 10 to the negative 3. Got 6.32 times 10 to the negative 8, and 4.5 times 10 to the negative 13. Now remember a minute ago I brought up how this value is really pressing close to where we're going to have the leveling effect of water. That's why we only know it out of the literature that I looked at out to 2 significant figures. So do notice that I have 3 sig figs in these two and only 2 sig figs here, and we should account for that as we go. Now I want to find the pKa's for these. I'm not going to worry about putting subscripts on this. I'm just going to set up a pK real quick. So equals negative, oops, doing this in the wrong order, sorry. Negative log of that value. Copy, paste, paste. Trim these sig figs back a little bit. See, there we are. Remember, whole number is not significant because we went through a log transformation. And in the log, the whole number is just telling me how many orders of magnitude I was off over here, or how many I was over here. After the decimals, those are significant. So here I've got 3 sig figs. Here I've got 3 sig figs. Here I should have 2 sig figs. Now I've got it. Okay, so those are my pKa values that I'm going to work with. Now, if we're doing a really fast and crude sketch, these tell me where I should have the buffer region. Because remember, when pH equals pKa, I'm going to have a 50-50 mix of the acidic and basic forms of whatever acid I've got. Now, the volume that I have there isn't going to matter because with the Henderson-Hasselbalch equation, I'm going to have concentration on top, concentration on the bottom. In the bottom of both of those fractions, I've got the same volume because they're in the same place. Those 2 volumes are going to cross-cancel, leaving just the number of moles, so I actually don't have to care about the fact there's a dilution happening at all right there. It's just a nice convenient thing to point out for us, and it'll come up again here in a few minutes. So if I'm going to do a quick and crude sketch, I'm going to do a little bit of clicking back and forth here. So 2.148. So halfway to my equivalence volume, I'm going to have a 50-50 mix. So right at this spot, I should be at pH of I just lost the number I said, 2.148. That's pretty close to 2.2. I'm just going to put my dot right about here. Right, remember, we're just doing a sketch. So I can get away with being just slightly crude about it. I want to be tight, but not totally perfect. All right. Now, generally the buffering region goes about plus or minus 1 pH unit. Let me get the dot bigger again. Now, I can't quite make plus 1 or 2 pH units here because of the leveling effect of water. So just knowing that there's a realistic aspect to it, I'm just going to kind of sketch it like that and have it dropping off. I'll come over this way about the same way. Now inside of here, I know for 90% of the range, of VEQ, I'm going to still be in the buffering range, right? It's once I'm out of that that'll break the buffering. Sorry, there it is. My mouse just stopped responding again. Trying to get the tablet to respond, and it's stopped. Okay, now I guess it's back. Here we are. Kinda. All right, now I'll just turn on the pen again. Hey, all that scribbling I was doing to make it show up finally showed up. Although I guess I could have just gone straight for pen and then used eraser. All right, whatever. It'll work. All right, so now that I'm getting about 90% of the way out of this range, it's going to start jumping up because I'm having it go between the spot where I had predominant form. Over here I had my predominant form is H3A. Now I hit the 50-50 mark of H3A and H2A single minus, right? So that's my predominant form now. Right here at this spot here, I'm going to be 100%-ish in the form of H2A, single minus. Now some of that is going to start picking up ambient protons. Yeah, that's not real. Let me just turn down the volume on that. There, that's better. So it can find some ambient protons from KW and reassociate. It can find some OH minus from KW and dissociate more, and then they're going to find each other and come back together. All that's going to be important in the equation we're going to get to in a minute. But right here, we can act more or less like it's 100% in the form of H2A single minus. So our singly deprotonated form. That's at least a good starting point for it. Now let's find out the pKa for our next one. We said that that was going to be 7.199. So about 7.2. Okay, trying to get my pen to work again. 7.2. So up here is 7.2. I'm just going to make a little line here just to guide my eyes in a second. I want to come over 2 units because now I'm at VEQ 1/2 again, right? So right here is the dot that I needed to draw. Now I'm just going to erase these. I just did that to make it easier on my eyes. So let's come over here and just sketch out a buffering region. So I want to come down about 1 pH unit before I get back to here. I want to go up about 1 pH unit by the time I get out to about here. And then it's going to start jumping up again. And it's going to start jumping down. Now I can just kind of connect the dots and sketch this real fast there. My third pKa is going to be, let's see, 12.35. So again, I'll come over here 2 more units. 12.35, just got in my eye. 12.35 is coming off the edge of the paper. So that's not going to work out great, but it's fine. I'll just kind of say, you see the buffering coming down here. Things above that pH, we're going to be hitting the leveling effect of water anyway. So we're probably not even going to notice this endpoint right here. Probably not going to be able to see it hiding there on the leveling effect of water. And from this point forward, every time we add anything more, we're just going to be saying, hey, we are now, let me point out, we're still in H2A right here. Then we got to the predominant form HA double minus. You'll see why I jump back to this in a second. HA double minus. Now after this point, we are fully in the form, getting fully into the form of A triple minus, so the fully deprotonated form. Right up until this point right here, we still have a little bit of the HA double minus. At that third endpoint, we've completely depleted that. We now just have A triple minus hanging out in solution, and every additional drop that we add, we're just adding more sodium hydroxide to salty water. So we're going to just have it keep on ascending toward pH of 12. So that gives us a quick idea of what the titration curve is going to look like. So now what we can do is we can actually substantiate this a little bit more and maybe even tweak the graphic a little bit by actually using some numbers. So that's the first thing I wanted to show you is how you can do a fast estimation of one of these graphs. Now I'll point out it can go a lot faster without all the explaining. I figure out my pKa's. I put a dot down at VEQ 1/2 for each of my pKa's. I flatten the range between them. I have a cliff happen right here, wherever it's jumping up between them. And then I just flatten it out at the top and bottom. And that's it. That's a fast way to sketch a titration curve. So that's all that we need to do there. But you'll also notice that all the spots I just said there actually do have specific equations that support them. So let's go ahead and jump into some of these equations. Now, let's start out with the case where we haven't added anything to it at all. So we're at 0 milliliters of titrant. Let me just write that down. 0 milliliters of titrant. Now notice I didn't put any sig figs on it because that's an exact value, right? I didn't add any to it yet. So let's go ahead and we can just figure out what the concentration of H plus should be, and then we can figure out what our pH will be. So right here at the very beginning, I could set up an ICE table, and I'll just kind of sketch it out really fast. I'm going to erase it really quick here. I'm not going to worry about doing all of it. We're going to have the H. For simplicity, I'm just going to write it as HA. That's H triple A, triple HA. And it would be dissociating into H2A single minus. I'm just going to draw it like that. And we'll have our H plus. Now, we start out with our formal concentration right here. Make that look more like an F. And we didn't have anything here that was appreciable. Now you might be like, well, wait a minute, didn't we have to care about the concentration of H plus from the autoionization of water? I'd say for just plain water, sure, but don't forget, right now, we have the phosphoric acid in it. And that's a much higher concentration than any of the H plus we have to worry about from the water. So we're just going to ignore that because it's insignificant compared to our values. We're going to react away some of this and make some of this and this, which finally gives us this form of F, formal concentration, minus X, X, and X. And then we go ahead and we start setting it up in our Ka value. And notice that this ends up being a really fast and useful expression. We get, let me specify that. Ka equals, we're going to have our X squared on the top. Remember, the products go on top. Both those are X, so we have X squared. Over formal concentration minus X, coming from right here. So this is an expression we can just remember as the starting point anytime that we just have the acid in equilibrium sitting around. So that's going to be exactly what happens when we have 0 milliliters of titrant around. It's just going to be this expression. Now, let me go ahead and I'll pause for a second and open the equations manual. Okay, and I'm back, and you can see I've opened the equations manual, and I've jumped down to page 3 for our acids and bases segment. You can see that right here we have the expression that we just wrote down a second ago. Ka equals X squared over F minus X. So this will be appropriate whenever you're at the very beginning of your titration curve. So from here, we just plug in our Ka value. We plug in our formal concentration. We solve the quadratic formula for X. And as a result, we find out what X is for each of these. Popping back over to, popping back over to here, we see that X will be the concentration of H plus. So now it's just going to be a matter of us taking the value for X, sticking that into our equation for pH, and now we've got the pH of that spot. So let's just solve that real quick here. So our Ka value at the beginning, it's going to be 7.11 times 10 to the negative 3 equals, we have X squared on top. Our formal concentration was 0.1000 minus X. So now we can just multiply this over to the other side. With it just being one decimal place, this is actually easy enough to do in my head. And if it's not for you, that's fine. Store-bought is fine, to be Martha Stewart about it, I guess. Oh, and then I still have my minus 7.11 times 10 to the negative 3 X. And then on the other side, I have X squared. So then I can bring all these over here to this side of the equation. So it'll be X squared plus 7.11 times 10 to the negative 3 x, c, minus 7.11 times 10 to the negative 4 equals 0. Yay, we have a quadratic equation. Now, the thing that people love to do, and the book does bring this up, is that we can make the estimate, then test the assumption that this is going to be a very small contribution. We could just treat that as being x squared equals 7.11 times 10 to the negative 4 and take the square root. What I'm going to do instead is I'm going to pause and I'm just going to type this into Wolfram Alpha and have it do the quadratic formula. Similarly, if you have a quadratic solver on your calculator, I'm fine with you using that during an exam. You can also still use the quadratic formula longhand, which is possible, and so we've done lots of times in our lives, but not the most fun. So let's go ahead and try that. Okay, so I'm just going to look over on my other monitor to see what I need to type in here. So I have x squared plus 7.11 times 10 to the negative 3 x minus 7.11 times 10 to the minus 3, times 10 to the minus 4 equals 0. I'll just hit enter on that, and Wolfram's just going to go ahead and graph that for me. And then if I scroll down a little bit, I can look at the roots. And for that, my root is 0.0233455. Now, I know that I'm going to be limited to 3 sig figs on this one, so let's just pay attention to the first 3 sig figs and maybe grab one for rounding protection. That's going to end up rounding up to a 5, so it'd be 0.02335. 0.2335. 0.2335. There we are. Oh, 2.335. That number doesn't have a unit because it's just a number. When we plug that back into here we are, we know that it's going to be the units of molarity. I'm just going to go ahead and throw a molarity on it right now. We'll do the negative log of 0.02335 moles. Actually, let me fix that right now. I did say that was not a significant figure. So that's molarity. So now I just have to go ahead and plug that into my calculator, which is right here. So what did I say? It was equals negative log of 0.02335. Hit enter, and I get that pH to be 1.6317. Now, we now have that at 3 sig figs. Remember, only decimal places are significant, so that would be 1.632. So 1.632. .632, and so we would go ahead and plug that in on our picture up here. You can see here that I did an okay job kind of just ballparking that, just guesstimating it. And that's basically what you can do on the sketching, but if we're going to do it numerically, this is how we'll do it there. Now notice that at this spot, we have a special equation. And let me draw it differently, and let me use a different color so it's easier to follow with our eyes. Hopefully, well, actually, let me go for something other than green in case somebody's colorblind. Like, hopefully nobody is, and then I'm like, well, it's easy enough to change, isn't it? So I'll use purple and just bring it up here so that it's easier for me to label. So at that spot, we can say Ka equals x squared over f minus x. That's our key equation that we care about right there at the beginning, right? Okay, now as we start adding liquid in, then we're going to start getting to the point where we can actually have a buffer form. Now, to do anything in that buffering region, though, the first thing I need to know is what was my VEQ, number 1, so that I can figure out what VEQ 1/2 is, because that's where I'm going to have pH equaling pKa. So let's go ahead and calculate that volume as the next thing that we need here. So I'm trying to erase it. There it is. All right, so let's come back over to here. Let's see. So So I'm just thinking through. Yeah, I do have the information on the next page. All right, so let's go ahead and do a calculation for what our endpoint is. Now, realistically, you can do this in either order. The first one that I usually do is finding VEQ, and then I'll solve for the no volume added. You can also solve for the no volume added, then start worrying about once you start adding titrant. Both of them make logical sense to me, so it's totally up to you which one you want to start with as you're figuring these out. But now let's figure out the exact concentration, the volume needed to get to VEQ 1. Well, that's a pretty easy test, isn't it? So I'll convert my 100 milliliters. I'm going to do that fast in my head. It's going to be 0.10000. Yep, 4 zeros. And that's going to be in liters times my, 0.1000 moles per liter for my H3A. Notice how much faster that is to write than phosphoric acid. The A just stands in as the phosphate. It's a dummy anion. And it's also convenient that it accidentally kind of means acid as well in this case, but it's actually an A for anion. All right, so let's keep going. So this cross canceled. I'm in moles of H3A. Now I need to have my stoichiometry here. My stoichiometric coefficient is going to be 1 mole of H3A reacts with 1 mole of NaOH. But wait a minute, no, it's a triprotic acid. It should be 3, right? Eventually, yes. But we're focusing just on the first portion of the titration curve, and that's when we only have the first of these protons being titrated off of it. So I'm just going to keep it very contextualized in that spot right there. All right, so now we are now into moles of NaOH used. Now use the concentration of NaOH to get from moles to liters. You'll see I am being a little bit less rigorous than I often have been with labeling things. Like I didn't put my chemical species here and here like I usually do. I really am focused more on the titration curve portion of this. So I'll try not to be too sloppy though. All right, so my titrant concentration goes in as 0.1000 over 1 liter. And if you feel like it, you can grab your calculator and plug all this in. But let's face it, we already know these are equimolar for their concentrations. So it's going to take the exact same volume to neutralize it, right? So we're going to add 100 milliliters, and that's what the answer is going to be. And yeah, I already magically converted from liters to milliliters. So that's going to be the milliliters of titrant we need to get to VEQ 1. Now notice it's real easy to do this process if you had a different concentration right there, or if it was a different volume that you were talking about. It's really easy to update that calculation. It's one of the longer ones you did in Gen Chem 1 until you get to ideal gas law, but it's not like it's a long or hard one. So I'll leave that for you. Okay, so 100 milliliters is going to be VEQ 1. So let's go ahead and label that. Now, I know we usually don't place it on the graph. We usually place it over here in the margin, but that margin's already taken, and I know I'm not going to need this spot, so I'll just write it right there. Now I'm going to get looser with the sig figs down here just to make it obvious and clear for us as we're reading it. So 100, 200, and 300 milliliters. But those are, oh, all right, fine, I won't. I will be rigorous with my sig figs. There. Okay. Now notice that each of these VEQs, we're just adding that same portion of liquid again. I'll also point out that for the total solution that you have, you're going to have had, so at VEQ1, you dispensed 100 milliliters. You already had 100 milliliters. Your current depth is 200 milliliters. So that's how much we've added. That's the volume of titrant or volume of base. You'll often see it just written as VB on this axis in the textbook and other places. That's the volume of the titrant that you've added. Not the total volume in your flask. You have to remind yourself to think about what's in the flask if you're calculating your pH. Sorry, I just accidentally bumped my chair button. Let me get back up here so I'm not sitting on the floor. There we are. Okay. Now don't worry, from here it starts going a little bit faster. we've set the stage for these calculations. So, all right. Now let's think about what's happening over here at VEQ 1/2. Well, VEQ 1/2 is just halfway to 100 milliliters, so it's going to be 50 mils. There we are. Okay, so 50 mils. And that's going to be the spot where I have a 50-50 mixture of H3A and H2A, both in the buffering zone at the same time. So at that spot, we already know pH equals pKa. We didn't really need to do anything special there. That makes it really convenient. But that said, through this whole region here, we are in a buffering condition, right? We have an appreciable amount of both forms, both the acidic and basic forms. So we need to use the Henderson-Hasselbalch expression in this region. So let's come back over to here to remind ourselves of where to find that. And here's our Henderson-Hasselbalch expression. So pH equals pKa plus log of the anion over the acid. And I have a hard time remembering this one because it feels like it's backward when you look at this versus what the actual Ka expression is set up like. And that's deliberate. So what they've actually done here to make the Henderson-Hasselbalch expression, and I want to be real clear about this, this is just your Ka value rearranged and then with the log transformation applied to it. So log Ka, log H plus, log A minus, log HA. And when you have additions and subtraction and things on the other side, that just changes whether it's a positive or a negative and where you've got them in the fractions, right? So this is actually just our mathematic rearrangement. It's an exact rearrangement of the Ka expression. So there's absolutely no estimations being made here. This is just your Ka value being rearranged. All right, so Henderson-Hasselbalch. Now I'm just going to go ahead and throw this over in my other window just so that I've got it handy to make sure that I write it down right. I don't want to make mistakes when it's hard to edit them. What I would usually do in class, and you've seen me do this, is I'd copy the image and paste it into the PowerPoint. But I'm trying to minimize the amount of alt-tabbing that I do because that might mess with your bandwidth a little bit. Okay, now I'm going to bring the pen back over to this side. Here it is. And I'm going to just point out that in this buffering region, we have our P. Okay, sorry, it's not noticing the pen. Sometimes when I go backward, yep, there it is. Sometimes when I do that, it recognizes things again. So pH, and if my handwriting looks even worse than usual, it's because the pen interface is actually stretching between both of my monitors. So I'm actually having to write half the width that I usually write, and that's, not going perfect, but we'll make it through. pKa plus log A minus over HA. And I left it out of the concentration there for a moment because, as I pointed out at the beginning, for concentration, if I do moles per liter over moles per liter, this can cross cancel. So I can really think of Henderson-Hasselbalch as being either for concentration or for being for moles. Either one works totally fine. And so just to emphasize that, I'm going to leave it here in the most naked form as you see it, knowing that it can stand in as either one. Throughout that entire buffering region, this is an appropriate expression to use. At the spot where you have an equal amount of A minus and HA, those two numbers would cross out and give you the fraction 1. You take log of 1, which is 0, and at that spot you get pH equals pKa. So this is an even more special spot within it, and we drew that at the very beginning of this mega problem, right? Okay, now let's move forward one more. So on this one, notice that out here, this is the next spot we need to be thinking about. Now we can solve for exact spots along this, but we don't usually care. The spot we care about most is the spot where VEQ1 lies. And if you think about what's happened for VEQ1, this is going to be the same thing I said verbally a few minutes ago, but we're going to get into it a bit more mathematically. We are going to have a reaction with ambient OH minus moving the titration forward and deeper into H2A minus land, right? We're going to have H plus being found and pulling it back this way. Then the form you formed of each of these, they can encounter each other and they're going to revert it back to this, which means we have multiple equilibria happening simultaneously, meaning we need to go grab that systematic treatment of equilibrium. That's bad news. The good news is that problem gets solved so many times and with the same basic math to it that it's already just been solved, and it makes life easier for us, which is great news. So let me bring the equation booklet back over. Let's see if I can, hit the right buttons. You can see I have a lot of windows open. This isn't even the start of it. Here we are. So I'll bring this back over, make it full screen for us. So the next one we need to care about is this equation here. Concentration of H plus equals the square root of K1 and K2 and F plus K1 KW over K1 plus F. Now that might look pretty nasty, but remember, in one of these problems, all of those are constants. It's just a matter of plugging in the numbers and just plug and chugging it. And it spits directly out to your concentration. So you don't even have to then, do the extra stuff we saw on the previous slide. We can just go ahead and plug all this into our calculator with a negative log, and voila, you've got yourself a pH. Now, let me go ahead and throw this back into the other window again, because I'm going to walk us through doing one of these calculations for it. We'll use Excel for that as well, because, well, you've met me. All right, so waking up the pen again. There it is. Good. All right, so let's take a look at what's happening right there where we have 100 milliliters added. Now, the nice thing is, notice that that in the equation, in fact, here, let me just get that blank page. Actually, I'll just do this. I'll do it down here below. This is for VEQ. And let's just kind of tear the page. And underneath that, I'll do the work for this. We have concentration of H plus equals. Now I'm going to mention what each of these are as I draw them, pointing out that, yeah, all the things we mentioned a second ago are being accounted for. We have the equilibrium for the forward reaction, actually for the backward reaction, because K1 would be taken as backwards. We have the one for the forward reaction, K2, and they're both going to be modifying the formal concentration that you have present, right? And then we also have to account for K1 and KW, which is kind of turning it into the reverse reaction for K1, conceptually at least. I'm not going to worry about the exact mathematic transformation. We don't need to see the whole derivation here, and I'm not confident I could do it from memory. But it's in the book. All right, let me make that more of a K. So we have K1 again on the bottom, and another spot with our formal concentration. So you can see here, we're going to need to make sure we're careful with parentheses when we type this into the calculator. So let's go ahead and do that. Let's find out what the pH should be at that spot. Now for that, let me pull up Excel again, and I'll go half screen on here, so we can see it while I'm putting things in. So I have my K1 value and my K2 value. Those are right here, these two lines here, right? Let's also write down KW up here. And just to be completionist about it, K3, K2, and K1. Now you might be asking yourself, wait, why did he write K1 instead of KA1? Well, so just as a shorthand, since we're almost always talking about KAs, the book will often do it as K1 for the acidic form. When you convert it into KB, I do want to point out that you'll be numbering in the opposite direction. So if I convert this into KB, KB1 starts down here, KB2 is in the middle, and KB3 is up here, because you're always counting from the end that you're talking about. Here we're talking about the acidic end, so we're counting from the acidic form. Here we're talking about the basic form, so we're counting from the basic form. So we could calculate our KB values over here if we needed to. We don't, but I wanted to point that out for you so you have that bit of notation polished as well. That is one of the things that I want to make sure people understand when they're doing these calculations. Okay, so just to clean up things, I got rid of that. Now here's what I like to do for a more complicated problem like this. I'm going to do that first term by itself. I'm going to do K1 times K2 times my formal concentration, which I didn't actually mark anywhere. I should. Actually, here, let me just do that. Formal concentration, and we said that it would be, right there at the very top, 0.1, and I'll just go ahead and fix it sig figs. Okay, it's hard to do with it half screen, so I'll do it from here, format cells. And all right, we'll fix it here. So we've got 4 decimal places. No, there we are. Yeah, that'll be 4 sig figs because it's in scientific notation. Actually, I'll just put it back in a number. There we are. There's my formal concentration. So let's continue doing what I was doing a second ago. So K1 times K2 times formal concentration. Now we'll do the second term. So the second term right here, K1 times Kw equals K1 times Kw. Okay, and then on the bottom of the fraction, it's going to be K1 plus formal concentration. And you see it doesn't change it very much. That's what we'd expect. Now, the reason I like doing it piecemeal like this is now I can come over here and I can say, great, on the equation that I have here, I know I'm adding these two together. So let's just take that plus that. By breaking it out this explicitly, it's harder for me to get lost in the weeds, thinking that I'm just multiplying everything. I'll just leave that alone. Okay, so this is the top part of my fraction. That's the bottom part of my fraction. So finally, I'm going to say top part of my fraction divided by bottom part of my fraction. And the very final piece of that is the square root of everything inside of the fraction. Everything under the square root, rather. There we are. And I'll get that value. Now let's just go ahead and pull this all together into one equation. And I'm going to show you this little trick. I've probably shown it before, but I'll do it anyway. See how it's pointing at cell E8 right here? I'm just going to escape, come over here to cell E8. I'm going to click into here, highlight these. I'm just going to cut that. Actually, I'll copy it. I don't like cutting. So we'll do copy, escape, come over to here. And where that was, I'll just put parentheses, paste it, close it, and make sure the number didn't change. It didn't. Things are looking fine. Good. Now let's make sure that that's really working. If I delete this, this shouldn't change, and it didn't. So now I can come into here and say, okay, now I'm pointing at the blue and the red. So let me come over here and grab the blue, copy, escape. Come back over to here, find the blue, open, paste, close, enter, didn't change, good. Let's test it. Sure enough, it didn't change. Highlight these, copy, escape. Now where that was, open, paste, close. Still didn't change. Life's good so far. And finally, I'll go ahead and just take this piece here, copy, escape. And on the bottom of the fraction, I'll just say, great, open parenthesis, paste, close parenthesis, and no change. I delete this, life is hunky-dory. Last thing I can do is apply the square root. I can actually just do that right up here in this equation, nice and easy. I've got parentheses on everything. Oh, no, I don't. If you notice, see how that front one is turning bold? Let me show with the pointer too. This one will flicker as bold when I cross over. See how it's showing me? It's helped me spot what the open and close is on my parentheses. Let's surround the whole thing with parentheses. And then square root. Ta-da! That is my concentration of H+. So at the equilibrium, when it's sitting there in equilibrium at the spot where I've added in my 100 milliliters. That will be my concentration at H+. Finally, I can go ahead and get my pH, negative log of that thing. And, okay, I'm not going to worry about fixing the sig figs right here. Now, just to make this easy, I'm just going to scoot this over to the other window. That way I can come back to this window that you're seeing, and I'll just write in what the answers were. Sorry, waking up the pen. Okay, so that all equaled 2.05 times 10 to the negative 5. And then when I did negative log of that, actually I'll just write the pH. When I did the negative log of that, I got 4.68862 blah, blah, blah. I have 3 sig figs. So if I don't want round off error, I could leave a 6 down there. I don't care about round off error because I'm not really going to use it for anything. So I'm just going to go ahead and truncate it right there. So 4.689. Let's see how I did in my sketch. 4.689. Sorry. So 4.689 is my pH. And that was going to be right about here. And yeah, that actually looks to be right on the line for V equals VEQ1. Now, of course, so does this, and so does this, right? But notice how it looks really in the center between the two ranges. Oops, sorry. It wasn't liking the eraser button there because I lost my pen. All right, get it back to pen. And, all right, clean. Oop. Good enough. Okay, so we have this endpoint. So notice we just have to plug all those numbers in to solve this one. And it's really annoying. When you're doing it numerically, you've got to use this equation. This equation right down here. Oops. The good news is, and let me bring it from the other window again. Let's see. And it likes to lose where exactly I'm at each time I do this. When you solve for this whole thing, you will get a number that is very close to a different but similar number. Now, if you've had a biochemistry class and you've talked about amino acids and you've talked about things like doing a capillary electrophoresis or a gel electrophoresis, you've probably brought up the term isoelectric point before. If you haven't, that's where it comes from. Don't worry much about it, but I will point out these numbers will be very similar to each other. So let's see just how similar they are. I'm going to bring the Excel back over. Notice it's just saying that as to find our isoelectric point, I can just take the average of this and this. Yeah, I know I can add them together and divide by 2, but average works the same way. So I'm just going to do that, right? Mathematically, they're equivalent. One's faster to do on your calculator. This one's faster to do in Excel. So I found it to be 4.67. Let's remind ourselves of, wrong way. What did we have with rounding over here? So is it numerically identical? No, but these two are pretty darn close, aren't they? So when can you use them? You use this one when you're doing an exact calculation. You use this one to ballpark where the point should be when you're sketching. So my first run through here, I did a pretty good job getting that spot right because I already knew where to look with my eye. Notice how before I had done this sketch, I put this dot and I put that dot because pH equals pKa. And I'm just going to go halfway between them and put the dot there. That was all I did there visually. So when you're doing your sketch, you can do the same thing. That's a great way to do it. Now for the second range, we do the exact same thing. So numerically, pH equals pKa. Now, if we were solving it for a certain volume along here, and we aren't going to do that when we're making a titration curve sketch like this usually, but you might do that in the homework set. Now you're just going to do the same thing. You're just going to actually solve for how much of your acid you reacted into the basic form by adding in the NaOH. So if your formal concentration was 0.1 molar, you say, okay, so how many moles of my, pointing at the wrong one. if I have that much formal concentration of both forms of phosphoric acid. We say, yep, it's 0.1 here. Got it. And they say, great. So how much is it if I go 50 milliliters more? Actually, no, 50 milliliters takes me there. 25 milliliters more. So that would be at this point right here, right? So 25 milliliters more, we say, okay, fine. So I put in 25 mils. I reacted away. Well, since it's 25 mils out of 100, that's a quarter of it. So I reacted away a quarter of it. I go through the math and I figure out, okay, so 75% of my moles are in the acid form. 25% of my moles are in the base form. I plug that in a Henderson-Hasselbalch right down here. Plug in my pKa, and I solve for pH. Not hard to do, just not really relevant for our time here. I mean, I don't want to make this take more than the hour 15 we have for class anyway, right? But that's how I'd solve the exact spot here. Now, you will have that in your homework set at some point. I think it gives you like 8 points to solve along the titration curve, just to make sure you can do them. But now that I've explained how we do this first part, it's going to be redundant to do it here on the second one, right? Because everything still works the same way. I'm here in the buffer region. Finally get out here, and I still have a forward pull and a backward pull because I'm going to have H2A, which still has 1 proton on it. It can still lose the proton. It can still gain a proton and turn forward or backward into its forms. And those two can react with each other again. And yeah, systematic treatment of equilibrium. We use the exact same equation that we did down here. We just update our K values. So instead of K1 and K2, now we're dealing with K2 and K3, right? So that's all you got to do for updating that calculation. So hopefully that's good. I don't think we need to go through a full calculation of that one. We've got an example here. You saw me go through the spreadsheet way of doing that to just compile it all together. Obviously, you can do it on a calculator or with pen and paper. I was just trying to emulate the skill of doing it on pen and paper, the simplicity, on a spreadsheet, so you could see how everything worked and how you could make these calculations bulletproof for yourself too. On the exam, you'd probably do that pen and paper style. Sorry, a little coffee grounds there. Okay, so that would be how we'd solve the same position out here. But out here in the third range, and here's where I have to get a little bit hand wavy because I didn't leave enough room up here to draw the aftermath so well, and even then the leveling effect of water was going to create some problems. But let me just sketch out a different one for a second here. Suppose that our titration curve was a bit more, that's ugly, okay. This is going to be a really tough one to pull off, because like I said, all of the side-to-side wiggliness is amplified since it's 2 monitors wide. I'm actually using 2 hands to hold my pen as I did that. Okay, so we'd have, let's say we had a titration curve that looked more like this. Yeah, I know those buffer regions should have more curvature to them, more slope, but it's all right. So here is VEQ number 3, right? Remember back here for VEQ 2 and 1, we were bringing up that you had the forward and backward reactions still happening, and with the predominant forms were in each range, right? The predominant form centered on this spot was H2A, going from here to here, a single minus. And then I had HA, double minus, as the predominant form from here on out to the buffer range right here, right? Well, then now I've got H3A as a predominant, sorry, I'm saying it wrong. I start getting A triple minus. There we are. Hard to make my tongue and brain work sometimes, right? And notice there's no more protons there. It can't really reform in the same way. So we're going to have to use a different calculation for your final endpoint, or final equivalence point. Now, notice that I went straight to doing a polyprotic titration here. What if you wanted the simpler thing that happened like 2 chapters ago in the textbook? Monoprotic titration. Basically, that's what you're doing now. This section forward is a monoprotic titration, right? You only had 1 proton left. The form you started out with right here was HA double minus. So it's a monoprotic titration that eventually turns into the predominant form of triple minus until you use up the last little bit. I'll just do it like this. Here, let me make it like this. Emphasizing that it's the predominant form, let's make it Godzilla-sized. And then ant-sized, let me point out, yeah, there's still some HA2 minus around, but we're turning it all into a 3 minus as we move forward from the buffer point right here, right? From the center of the buffering range, we're depleting the tiny bit that's left until finally, in this last moment, all that's left is going to be the basic form. That means throughout this buffering range, everything still works the same as for our previous buffering, where I showed it explicitly and mentioned it quick in passing. But out here for the very final one, for a polyprotic, and for the only one on a monoprotic, what we're really saying is, when you finally hit the endpoint, you hit the final endpoint. And in the final endpoint, the only thing left behind is the base. So how do you solve for the pH there? Easy. Right here is exactly the same thing as right here. Oops. Oh, there goes my axes. That's all right. We're going to get rid of this in a second anyway, so I got some room to write, right? We're going to treat it just like the form at the very beginning. It's just now it's a base. It's 100% in basic form. So what are we going to have there? We're going to have all of my formal concentration in the basic form. Ooh, except for one little tweak. The formal concentration, we know that now all, let's see how many we had. We said it was 0.010000 moles at the very beginning, and all of that was in the form of H3A, right? We just said, cool, and at the end of it, we've reacted all of that away, and now it's all in the form of A triple minus. But what do we have for volume? We have the initial 100 milliliters. We added 100 milliliters to get to the endpoint 1. We added another 100 milliliters to get to endpoint 2. We added another 100 milliliters to get to endpoint 3. We now have 400 milliliters sitting down here in this flask, right? Because we added 300 from here. Oops, keep writing an extra 0. We had 300, just to emphasize it, we had 300 going into the flask to get to VEQ3. We also had the original 100 down here in the flask, so we need to figure out what the concentration of the base is. So what we need to do is adjust the formal concentration to account for the dilution. Boy, I just used a lot of loaded capitalized words in that sentence, didn't I? We have that number of moles over the new volume, and that will give us our new formal concentration. In other words, the formal concentration updated, call it F prime, is just going to be number of moles in the formal concentration that you had originally divided by your new diluted volume, which you could think of as V initial plus V titrant. That's all that you're doing is updating your formal concentration. And then we can plug it into the equation. Now, why am I alt-tabbing my way over to something? Hey, look at that KB expression. That sure does look like something we were just talking about, doesn't it? That's all that we're doing. We're taking KB for that final Ka value. So remember, you got to convert it into KB. We're now counting from the base end, so this will be KB1. We solve for x squared using the formal concentration. So let's go ahead and take a look at what that will be. Let me come back over here to Excel for that. So K1 is Ka1. K2 is Ka2. K3 is Ka3. Counting from the opposite end, we start with the base. This will be KB1, KB2. Okay, my backspacing skills sucked there. Okay, and KB3. The only one I actually care about right now is KB1. Now you know the fast way to solve for this one? Let's It's me saying, all right, I've already got pKa, and I know pKa plus pKb equals 14. So let's just do 14 minus that value, and I'll get my pKb. Actually, let me move this over here because things are getting a little crowded and a little less labeled, right? I'm going to scoot this down here from before. All right, so I'm going to move this over too because that's actually what I'm trying to get to eventually, right? So I just found my pKb. So that's pKb1 right there. I'm just not going to make individual labels coming down the table. And I'm going to leave these two blank because I just don't care. Although I guess not. Why not? It's fast. There. I just realized I've already done the calculation, right? And then all I got to do is fix my sig figs so that I don't cry myself to sleep at night. And as we expect, these add up to be 14. In case you never noticed it, down here in the bottom of the toolbar, it may already say sum and tell you 14. And if not, you can right click and tell it, turn on these little calculations here so I can see them fast and easy. It makes my life convenient. Can't do anything with it, it just makes it convenient, right? Okay, anyway, so we now have pKb. We need to convert that into a kb. Let me scoot that over one more cell now that we have the room for it and things are well laid out. You can see here that, well, that's right, we just typed those numbers. To get to the pKb, we now need to do the opposite of negative log, right? So we do equals 10 to the, let's see, where's my caret symbol? There we are, to the negative of that value. Okay, thank you for rearranging everything and popping out a scientific notation. Let's just make that scientific notation, just to make it more polite. And let's just scoot that back over. Still not quite the same, but I'll live with it. Okay, now let's do a fast reality check. Does that look right to me? Yeah, it seems about right. It's going to be us acting as a fairly strong base, right? Now I could even go ahead and just complete the thought process upward. And sure enough, everything is calculating out about the way that I expect it to. So that's seeming okay. So I've got my KB1 counting from the base direction. All right. Now we said that, I'll just kind of retype it here. We said formal concentration adjusted is going to equal, let's see, I said the moles divided by the dilution factor, but we can also just do it as a quick dilution factor. Sorry, I'll just do it that way. So this is my formal concentration, and I now know that I'm up to 400 milliliters. So let's just put a spot for V final. And I'll put that in liters. That'll be 0.4 liters. All right. Oh no, it's going to bug me. I like things to be like I expect them to be. There we are. So 0.4 liters, there we are, with sig fig showing up again. So we find our new concentration, so F prime in molarity. I don't actually have to solve for moles and undo it. I can also just do it as a dilution factor. So I started out with this concentration times the original volume, 0.1, divided by my new volume. And let's give that a quick reality check. Again, I'm just going to take it out of scientific notation. So does that match what we'd expect from just thinking it through? Well, if I take this and I dilute it 4 times, yeah, that seems right. So that's my new formal concentration. Now remember what the equation was. We said that, in fact, let me just go ahead and get that over here in the window. And let me think if there's a clever way to do this. Kind of is. All right. And I'll just move this over. Good enough. And I'll just bring this over. Almost good enough. And now it's good enough. Okay. So we just got to solve for this. So we set up our KB. And we just solved KB is right there. And hey, look at this. We're going to actually have to do this as a quadratic equation again. So I don't really need to do anything in Excel. What I need to start setting that up as a quadratic. So let me just go ahead and I don't need this open anymore, so I'll close it. I'm also going to toss this over into the other window so I can refer back to it, and I'll go ahead and I'll write it out. So on this one, KB, oops, sorry, it's doing that. KB equals x squared over formal concentration adjusted minus x. We set that up. We get KB. KB was 2.22 times 10 to the negative 2. It's like somebody got stuck on the 2 button there, but all right. So that's our KB. We have x squared on the top still. And remember, this is just a fast version of skipping the ICE table. That's all that we're really doing, setting up this expression here. All right, now we have, for our bottom, we have our formal concentration, that's a 0, not a 6, 0.025 out to 4 sig figs minus x. So now we go ahead and we plug that in and we do our quadratic formula. So that was me missing the button again. So again, I'm just going to throw this in the other window and I'll type it just to save you from having the screen updating like crazy. And man, I'm going to have this be exactly the length of a normal class. So I'm working this out pretty well, I think. I hope. Hopefully not everybody's just playing me at, crazy, ludicrous speed. All right, so we have x squared over, parentheses, then I need 0.025 minus x, close parentheses, and good. Get our quadratic roots. And then when I solve for that, it's got, let's see here, the quadratic root is giving me 0.0149425. And I need that at 4 sig figs. So actually, no, I'll be at 3 sig figs because of the KB. Because remember, our Ka, actually no, I should be down to 2 sig figs. I've kind of lost sight of that. Okay, so I'll be down to 2 sig figs there. All right, so we'll be at 0.015 molar. So 0.015 molar for x. So x equals 0.015. Now remember though, and here's where people get confused on this spot. If I were to make an ICE table, what am I dealing with here? I'm dealing with the base form. I now have A triple minus plus H2O yields H A double minus plus OH minus. So we're not solving for H plus anymore. Notice that this gets wiped out because it's liquid, right? This one we started out with our formal concentration, updated, minus X, got F prime minus X. That was the bottom part of the equation down there. Up here I had nothing, I ended up making X. Sorry, I'm skipping a step. Let me just be explicit. You got X there, meaning the X we just solved for here is the concentration of OH minus. So what's the fastest thing to solve for? It's not pH, it's POH. So let's do negative log of 0.015. And I'll just do it in the other window. It's pretty unexciting to see. Equals minus log of, it's also unexciting to see me typo and spell la instead of log. All right, so 0.015. So we get our POH to be 1.82, because again, remember, 2 sig figs is what we're down to. So POH equals 1.82. And as long as pKW is still 14, so as long as we're at normal temperature, that means if I subtract 14 minus 1.82, I'll get my pH, and I can actually do that in my head. It's going to be 8, 1, 4, 12. There it is, 12.18. So we have 12.18 as our pH. Yeah, not pOH. As our pH. So on the titration curve, our last dot should be at 12.18. So we come back up to here. There we are. And so right here, this spot should be at 12.18. And my graph just didn't go quite high enough to make that happen. So 12.18. Now what about in the aftermath? Remember, it's just salty water. So you just take whatever volume you've got and you just keep on calculating your dilution factor on the sodium hydroxide, and you plug it in, you see how much sodium hydroxide you've got, and you'll just keep on adding more and more base to it and having that base go up. Okay, so that's how you'd find the pH at any of these spots on the titration curve. Now, one last thing I'm going to throw in here, and this is where I will go just a bit more than the hour 15, but I think it's going to be helpful. If I were to try to work this backward to identify what an acid is, what I'd do is I'd say, let me just clean this up a little bit real fast. In fact, I realized I could pause while I was erasing. All right, so how am I going to identify this acid? Well, let's see. Let me just see. First thing I'm going to do is I'm going to say, hey, I see a cliff. I'm sorry, let me do a different thing. Let me do the highlighter so you can see where I'm going to be looking. That'll be better, I think. I see a cliff right here. That cliff has to be a pKa. Does it mean there can't be a pKa hiding over here where the leveling effect is happening? No, it doesn't. Now, depending on what that pH is right here, I may or may not be worrying about it. But either way, I'm going to spot that there is definitely an endpoint right here. There is definitely an endpoint right here. I actually can't see the endpoint right here, right? It's hiding the leveling effect. So what am I going to do? Well, now what I'm going to do is I'm going to come over. I can identify my VEQs. And if it turns out that I see a long plane here and then a gap that's half as wide right here, that's telling me, oh, there are actually two pKa's happening in here. I just couldn't see one of them because it was hiding the leveling effect. So it would have taken me the 200 milliliters, assuming the numbers are the same up there, 200 milliliters to get to the endpoint I could see, meaning there was actually an extra endpoint that I couldn't see. So now I know that what I'm talking about for each of my pKa's, right? So I can start coming up with numbers. I can say, all right, so we come to halfway between those, and I can see that I've got a pKa of about 2.18, and I'm sorry that that's yellow on white. I'm just going to narrate it and write it down to make it clear what I'm doing. So 2.18, and then up here I've got one that's obviously at 7.12 or 7.2 or something like that. I can say, well, I might have another one up here, question mark, and if I do, it's greater than 12. So I'm going to look at a list of acids and see, do I see any acids that fit the bill? And sure enough, when I get to phosphoric acid, I say, oh yeah, check it out, phosphoric acid. It's got a pKa of 2.15. It's got another pKa at 7.12, which is pretty close to the 7.2 that I guesstimated from the graph. And then there's another one hiding up at 12.35, and oh yeah, that's totally in the leveling effect. And I'd say that makes sense as an identification, so I'd call it phosphoric acid. Now, what if let me just make one up. And I will go back to pen for this real quick. What if I did have something like I was just describing a second ago? What if I had something that looked like this? Now, I don't think we would. But what if we did? I'd say, oh, well, I can see that I've got, and of course these should be straight lines, so please just bear with my art, or lack thereof. Okay, that's definitely a VEQ. I don't know the number. That's definitely a VEQ. Hey, check it out. These are however many milliliters apart they are. And hey, check it out. If I come over here, there must be one right there too. So this must be VEQ1. This must be VEQ2. This must be 3. And Man, it levels off like right here, so something's up. Actually, I'm probably just being bad with my art, but whatever. I'm not going to erase it. I'm just going to go with it, okay? So I can say from this, I need to go look for a triprotic acid, and I can say for that, one of my pKa's is going to be here. I'll look at whatever number that is. One of my pKa's is going to be right here, not right here. Remember, the buffering region is where pH does not change much. Oh yeah, I didn't label this there. Better. Okay, so I'd say, okay, so I've got my other pKa, and it's right here. And I also figured out that there's another one down in here somewhere, but it's so acidic that it's in the leveling effect. So it's a really strong one. So maybe I'm looking for pKa 1 is strong. pKa 2, and I'm going to make up numbers here, is 2.5-ish. pKa 3 is 5.1-ish. Then I go look at a table and see, do I see any acids that fit the bill for that? That's how you would work this backward to do an identification of an acid qualitatively. Quantitatively, well, we could actually solve for the exact pKa's if we had numeric data. But most of the time, it's going to be more important for us to do it from the titration curve like this. Okay, so I'm going to leave it there. I hope this worked out well for everybody. I hope you have a great week, and I will see you when I'm back in person. Take care, and hopefully you find this useful.